Alright guys, so today we're going to be talking about acetal formation. And essentially what that is when we have a carbonyl, so that's either a ketone or an aldehyde, we can react it with a molecule that has an alcohol functional group. And this R here represents the rest of the molecule that the alcohol is attached to. In addition, we'll also use an acid catalyst to start off our mechanism. This will get us our acetal, which is where we have our carbon maintained here, and then we have two new bonds to oxygens that are also attached to the rest of the molecule that the oxygen is bonded to. So with our acid catalysts, the most common ones include hydrochloric acid, which is HCl, or we can also use sulfuric acid, which is H2SO4. So here is the mechanism as follows. So first, we'll bring in our carbonyl, which we'll use a ketone for this example, and we can react it with an acid catalyst first. So we'll use hydrochloric acid. The lone pairs on the oxygen will take that hydrogen and we'll move the electrons onto the chlorine right here. So now what we get is our double bond still to our oxygen, and then it has a bond to that hydrogen right there, so it has a positive charge. So now what we can do is we can bring in our ROH. It has two lone pairs right there, and that lone pair will attack our carbonyl carbon, moving those electrons onto the oxygen right there. So now what we get is our OH right here, and then we have a new attachment to an O right there. It has an R and an H. One lone pair, so it has a positive charge. So what we'll do now is we'll bring in another equivalent of our ROH, and it's going to take the hydrogen right here to get rid of that positive charge on this oxygen. So now we have an OH, and then we have an OR. Now because this mechanism is so lengthy, we can use some benchmarks or indicators to make sure that we're doing our mechanism correctly. So this molecule right here is called a hemiacetal. Where our carbon right here is attached to an OH and an OR. So now we'll draw the same molecule down here. And we're going to bring in our ROH that has these two hydrogens right here. Has a positive charge. And so this oxygen right here, this OH, it's going to take that hydrogen, it's going to get pronated. We're going to move those electrons onto our oxygen right there. And so now what we get is an oxygen with two hydrogen bonds, and then we still have our OR. So now we're going to take this part of the molecule and we're going to force it out as a leaving group, which will just be water. And the way we do that is we're going to take one of the lone pairs on this OR, we're going to form a double bond, and we're going to force this molecule out. So now what we get, bond's still there, and now we have a double bond to our O. And this molecule right here is called oxonium ion. So now what happens is that we bring in another equivalent of our ROH, and it's going to attack our carbonyl carbon right here, moving those electrons onto our oxygen right there. So now we have an OR, and then we have our oxygen here with our bonds to our R and our H. And it has a positive charge. So to complete the mechanism, we're going to bring in another equivalent of ROH. We are going to take that hydrogen, Electrons will get moved to the oxygen right there, and what we get is our final product, which is our acetal. So that is the complete mechanism and reaction for acetal formation. It is a series of protonations and deprotonations, and as long as you can stay on track with your benchmarks like your hemiacetal, your oxonium-ion, and ending with the correct product, it's really simple from there. So have fun with it. I hope this helps, and I will see you guys in the next video.